Hello everyone, my name is Dionysios Sourailidis and I am a PhD candidate at Aristotle University of Thessaloniki. I would like to present some of my work regarding nonlinear dynamics and namely applications of chaos theory to cancer. So in this presentation I will talk about chaos and its relation to cancer, mathematical modeling of a cancerous growth. We will also discuss a novel system first proposed by LaNSCom et al. And then we will extend upon it by adding some time-dependent perturbations in order to reach some conclusions. So a few words about chaos. Chaotic systems are just deterministic systems with extreme sensitivity to initial conditions and parameter values, which means that systems with almost identical initial conditions values will give completely different solution trajectories. So where can chaos be found? It can be found in many fields of study, including engineering, biology, astronomy, economy, and almost all physical phenomena have a chaotic nature, as a matter of speaking. Now, chaos also has many applications because of high unpredictability, determinism, circuit implementability, making them suitable for text, image, sound encryption, secure communications, robotics, and many more. Now, a few words about cancer. Cancer is a blanket name assigned to a complex network of interactions of malignant cells, which no longer possess specialization and control over normal growth. This network of malignant cells could be treated as a nonlinear dynamical system, self-organized in time and space, definitely not in thermodynamic equilibrium, indicating high complexity, robustness, and versatility. Now, how is chaos theory connected to cancer? So as you can see, the concept of modeling cancerous growth using dynamical systems was first proposed by Carol Newton in 1980. Many researchers continued and proposed newer and more precise modules, and as years passed. In the present work, we study an intriguing model that was recently proposed by LaNSCom et al. So, the LaNSCom model is based on a chemical network and describes the mechanism for avascular, vascular, and metastasis tumor growth. As you can see the equations here below. In these systems, the variable X, Y, Z represent the proliferating tumor cells in avascular, vascular, and metastasis phases, respectively. Also, parameter N represents the population of normal cells. Eta, the population of the host cells, and the I represents the population of immune cells, which are the T lymphocytes as well as the natural killer cells. So in the present work, we conduct a dynamical analysis of this system. Namely, the system is integrated numerically using the classical fourth order Runge-Kutta integration algorithm. For each set of parameters used in this work, the time step is always 10 to the power of -3, and the calculations are performed using variables and parameters in extended precision mode. For each parameter settings, the system is integrated for a sufficiently long time, and the transient is discarded. Furthermore, Lyapunov exponent of the system for the chosen set of parameters and initial conditions are calculated each time using the Wolf et al. Algorithm. So, running some simulations, I reached these results. You can see these are bifurcation diagrams for this LaNSCom system with respect to n for I equals 1, and then we change eta and increase it. And one can see what happens here. Actually, let's take a closer look. For lower values of the parameter eta, we observe that the system retains a periodic behavior for all values of the bifurcation parameter n. This can be seen, for example, in the first figure, where for eta equals 2, the system is periodic with period 1. As the parameter eta increases, the phenomenon of antimonotonicity appears, as can be seen in the second figure. And for eta 3.5, And for, yes, in these cases, the system starts from period 1, and then the period begins to double for values around n equals 3.5, going up to period 2, 4, and then 8, as you can see in the charts below. And then it follows the inverse procedure. This is signified by the characteristic formation of a bubble shape in the bifurcation diagram. As the value of eta increases even more, the chaotic behavior of the system becomes much more complex. Taking a look at the bifurcation diagram shown, yes, in the last two figures, the plethora of chaotic bubbles are observed. Now, this was the initial system that was first proposed by Llanos Perez et al. But also, Jaime et al. In 2018 proposed a slight variation on this module. And it goes, they did something like this. It's known that the immune system plays an important role both in the inhibition and in the progression of tumor growth. And the application of therapies that directly influence the immune system has been effective, as well as chemotherapies that favorably affect the anti-tumor immune response. Now, for this reason, for our work, we simulate a perturbation by adding the term A sine squared WT to I in order to simulate the effect of an immunotherapy or chemotherapy on tumor growth. A and W were used as control parameters. A represents the amplitude of the perturbation and suggests the intensity of the treatment, while W is the relationship between the frequency of perturbation and the autonomous frequency of oscillation. One can see here the equations below. If you look closely, this was all just one term in the previous equation. It was just I. Now we added this perturbation here and here. Moving on. So what we did before, in order to numerically integrate the system, we follow exactly the same procedure, but we change the model. So this was done in order to generate the bifurcation chart. So one can see this. This is a bifurcation diagram with respect to A for I equals 1, eta equals 5, and n equals 4. This is another case where I equals 1, eta equals 8, and n equals 5. And this is a third case where I equals 1, eta equals 8, and n equals 6.5. All right. One can note the emergence of various phenomena here. Of course, the anti-monotonicity is present as well. We also see boundary crisis and also hysteresis. And to be more specific, in the third chart here, we notice the hysteresis right around here. All right. So now let's try substituting the sinusoidal signal with a square one to see what changes. So to extend upon the previous model, we tried inserting a different signal than the one Jaime et al. Used, namely a square signal. So the system will take the form right here below. As you can see, this one was with in this place there was a sine squared. Now it's a Heaviside theta function in order to simulate the square signal. So, and once again, we follow the same procedure as before in order to obtain the bifurcation charts. So we obtain this, which is a bifurcation diagram with respect to A. For I equals 1, eta equals 5, and n equals 4. And yes, one can see that after switching the signal from sinusoidal to square, many interesting phenomena arise. One can note the crisis phenomenon. That is when the system repeatedly and abruptly exits or enters chaos, as can be seen from the crisp changes in the shape of the bifurcation diagram. Also note, of course, the anti-monotonicity again. This is when the system enters chaos by doubling its period and later on exits it by the inverse procedure. And also there can be some instances where boundary crisis makes its presence known. As you can see here, you have the internal crisis. Here you have boundary crisis, anti-monotonicity, period halved, and then it goes back to chaos again. Boundary crisis, and then the period is again halved, and then it returns to 1. This is the anti-monotonicity again at work. And we also acquired another simulation here of a bifurcation, and this also emits some interesting phenomena, like anti-monotonicity again, of course. You have a boundary crisis again, here where it's abruptly cut. And one can also note the hysteresis here, around where A equals around 2.5 or so, or maybe even less. So, in a nutshell, it is made evidence that simulating tumor growth with dynamical systems leads to witnessing many already known interesting phenomena of chaos theory, and is worth exploring further in order to generate more accurate models of tumor growth. Thank you very much for your time.